bracket. So let's see if we achieve this goal, and I think it's achievable. Let me remind you where we stopped on Monday. We were looking at these videos, remember, showing the netting for ductile materials, and we looked at this stress-strain diagram. So here, we are looking at what has happened to my voice. I don't know. We are looking at a stress-strain diagram, for example, for steel. It looks very similar to steel. And you see that you have linear elastic up to the point where it is typically called elastic limit or proportionality limit. Different people have different names for this, but it all means the same thing. And in some materials, you may see that you have a little bit of nonlinear elasticity afterwards, so yield actually starts a little bit higher. For some materials, they coincide. And then, depending on the material, you have some other features. And then if you're looking at engineering stress, that's the full line, the solid line. It reaches to a maximum, and then it goes down, and you have rupture. If you look at the true stress, which is, let's remind ourselves what that is. True stress is when we divide the force by the area as it is deforming. Think about the videos. Engineering stress, the solid line is basically divided by the original area. So if you look at the true stress, you see that it continues to increase. At some point, the rate of increase is very high, and then it ruptures. So you shouldn't be surprised why it ruptures here at a lower stress than the ultimate stress or the tensile strength. It's because we are actually looking at engineering stress. In reality, the stress keeps increasing. And when you reach a threshold, then you have rupture. We need to learn a few more parameters which are associated with this. And maybe if you have started with the homework, how many have started with the homework? Working? Great. You've seen that there are a few things maybe you still don't know what to do about. And that's what we are going to see today. So if you have this kind of stress-strain behavior, the material has this netting, and then it breaks. If you look at the cross-section, it's not very rough. You see this smooth plastic deformations at the cross-section. If you use your hand, you kind of see that it's not too rough. Now, these are ductile materials. So this is characteristic stress-strain for ductile material. What happens if the material is brittle? So here we are looking at a brittle material, and you see that you don't have this large elongation before failure. It goes up, in some material, shows some nonlinearity, in others it doesn't, and it just breaks. We have no warning, no extra deformation, etc. Now, in such situations, proportionality limit is up to the point where we have stress-strain is linear. Then you have elastic limit in some materials. Here, this portion is nonlinear, but still elastic. And I hope we all know the difference between the two. So, but the yield is not very clear. It's not very clear when it starts. People have developed an approximate method to find the yield strength or yield stress. And the way to do it is you take, let's say for steel, 0.2% strain, and you go parallel to the first line. So these two are parallel. And wherever you hit the stress-strain curve, you say this is yield strength. It's an approximation. It's something based on empirical observation. It's not like hardcore science. It's 0.2% for steel, and like for concrete, this is 0.02% offset. So it's called, then we call it like 0.2% offset yield strength. And then everyone knows how we got this value. Another thing I want you to look here is when you have brittle breaking, if you look at the cross section, you don't see this slope, you don't see the deformations, and it is much rougher if you touch it. So this is the difference between brittle versus ductile material. Make sure you know how the stress strain for each class of material would look like, and what are the typical characteristics of both each. It's also important to look at those examples, so have some ideas, like concrete behaves different from steel. Now, there are a few other parameters about this curve that I want you to know. One is strain energy density. When we look at force displacement diagram, you may have seen this before, that when you apply force and then you cause deformation, if you multiply force by the deformation in the direction of force, you get energy or work done by that force. This concept should be familiar somewhat to you, yes? So, when you do elastic or plastic deformation, this energy gets stored inside the material, and it is called the strain energy. So if you have a force displacement diagram like that, if someone asks you how much energy you would want to have, basically you have to calculate the area underneath up to a certain point that you have elongated, let's say, this bar. Why? Because this is basically the area underneath is force times displacement. Is everyone comfortable with this? That you look at the area under the force displacement to get energy? Something you should have seen. Look back at your strengths of materials books if some of this is not good, not very clear, or talk to me after the class. It's pretty much the same formulation. So the force that you apply, the energy that you apply, you apply a force, it causes deformation. The energy that you apply, the work, will be stored inside the material. And this is called the strain energy. And it's nothing else but the area under the force displacement curve. So if you look at this formula, this should be the sentence to memorize with. An integral is nothing else but an area. Okay, now strain energy density is closely related to that. It is the strain energy per unit volume. So it is some sort of a normalized version of a strain energy. If you want to know per unit volume, if you take one small cube inside your material, how much energy is being stored in that small cube, one by one? That would be the definition of a strain energy density. So, And the only difference is if you look at the area under, instead of looking at force displacement, now we have to look at stress strain. So the area under force displacement is strain energy. Area under stress strain is strain energy density. And you can convince yourself, right, if you multiply force by displacement, you get a strain energy. But then if I divide the force by the area, and I divide the displacement by the length, it is as if I'm dividing the strain energy by volume, isn't it? And this we happen to call, this turns out to be a useful parameter in we have mass density, a strain energy density. Now, there are two more parameters which are closely related to a strain energy density. And what we were talking about is pretty much an introduction to get there. So this is what I just told you. So strain energy density, the strain energy divided by volume. And instead of calculating the area under force displacement, you're looking at the area under stress strain here. So now that hopefully this is clear what this is, let's introduce these two parameters. Very simple. Modulus of resilience, or sometimes people just call it resilience, is nothing else but the strain energy density if you only consider the elastic part before yield. If you consider everything up to rupture, it's called toughness. So resilience and toughness are kind of two special definitions related to strain energy density. And they turn out to be very useful to decide what material to choose for which application. We are going to look at toughness, for example, when we talk about fracture mechanics. You see how important it is to know how tough the material is. So something that students sometimes make a mistake is like they think tough and they think strong. Because in everyday language, this is kind of what, if someone is tough, he is probably very strong. Doesn't look like me. But but toughness actually in mechanics of materials, it means that you are able to take a lot before failing. And if you think about people also, people who are really tough, like real tough people, are not people who look stronger, are people who are able to deform, they are able to take a lot before failure. So something to maybe to help you remember that toughness is not like the maximum strength, it's how much you can take in your life before failure. Now, it's very important because different materials have different toughness behaviors, and it affects very much how we choose them for which applications. Here you can kind of the difference between ceramics, metals, and polymers. You've seen these classifications a few times already. So ceramics are very strong, but they're not tough. Metals, they are not as strong as ceramics, but you see they have much larger toughness. And then you see polymers, they elongate a lot, but they're very, very low in strength. So at the end, they are not very tough. So to have toughness, you kind of have to have some level of strength, but to endure a lot. Just like in life, I guess. I guess I told you already that I think a lot of concepts in mechanics of materials apply to our lives. So we can use it to see how we feel. And then if we compare now, instead of ceramics, metals, and polymers, we look at brittle versus ductile. You see that ductile materials are tougher. And here is important. Brittle materials, most of their toughness is actually in the form of resilience, elastic. But in ductile materials, we have elastic, let's say up to here, this is elastic, and then you have plastic, after the plastic deformations. Any questions about any of that? So now, we do a couple of examples, and there is one important example at the end, so we should try to be more efficient today. So one example is you have a piece of lumber, you are putting it in tension, and here is a stress-strain curve. So here it is a super brittle material. You increase the stress, and at some point it breaks. You want to see what would be the ultimate elongation if you have the ultimate, this is U is for ultimate stress. Take 30 seconds, solve it. By now you know how these examples work. So the point here is to realize that since the relationship is linear up to failure, actually sigma u, the ultimate strength is right here. So the ultimate strain is here. That's kind of what relates to what we were talking about today. And then you want to know how much it deforms. It's uniaxial. You should be able to get this in less than a minute. So we want to calculate the strain, and from a strain, elongation. I need to see some correct answers. So just calculate the strain first. I know it's early in the morning. Because it's linear, we can do that. So we just calculate the strain and voila, this is what we get. I saw a lot of correct answers. Pay attention to the units here. So when you go from mega to giga, there's 1,000, a factor of 1,000. And then hopefully we all remember that 1 meter has 100 centimeters and those sorts of things. So again, the point here is that the wording of the problem. So if you didn't have this little figure here, and you saw that it says up to failure, we have linear relationship and ultimate strength is this much, you kind of have to figure out that it goes up to 100 megapascal linearly. So this is a brittle material. Maybe you want to just write that it's very brittle. Because it goes and it snaps. For example, chalk is like that. So if you have done this many times, but if you break it, and I cannot break it, you see that the surface is kind of very similar to what I showed you earlier for brittle materials. This is how it looks like. Now, next example. Now here we want to exercise those definitions. We are looking at the stress-strain diagram, KSI, and the strain is inch per inch, which is similar to saying it has no units. So this is for a grade 40 mild steel. Mild steel is a steel which doesn't have much carbon. So it's very ductile. You're going to see that soon. And now, I want you to calculate the resilient modulus and strain energy density when a specimen is loaded up to 0.007. So, resilient modulus is the area under the stress-strain curve up to the point when the material is linear elastic. This. So first you need to talk to yourself and say, okay, I know what the resilient modulus is. It is area under the stress-strain curve up to the yield stress, or yield stress. And then the rest is calculation. It's a triangle. Hopefully we know how to calculate. So I need to see a few correct answers with the correct unit. Also think about the unit. I forgot to emphasize that when I was teaching it. I've seen one correct answer for A and B. calculate this area. For part B, we need to calculate the whole area up to this point. Why up to this point? Because that's what the problem is asking. So it includes the linear and the first kind of plastic deformation. That's very plastic. So that means you keep the force the same, but the material keeps deforming. Right? So this is the first part, the triangle, and then that's the square. And the unit. The unit is the unit of sigma times the unit of epsilon. So it will be simply psi. Has to be. Now the last example, which is kind of a little bit different, and what I have put it there because it's important in review of mechanics of materials. So it's kind of something different. Okay. I think everyone is. Now the last thing I want to us to review together is a little bit different. So in the beginning I said our focus will be mechanical loading, but this is thermal loading. I think that you have seen this in mechanics of materials, but when we have temperature change, that creates strain. And the proportionality factor is something which is called coefficient of thermal expansion. Has everyone seen this before? And it is here, let's say, degree centigrade or Fahrenheit. And here you can see the range of, let's say, alpha for steel. Now, when you change the strain, the temperature, you create a strain. This is the most important thing for you to remember. You do not necessarily create a stress. And I have an example to show you what I mean. So remember, just think about, I don't know if has ever happened to you that you're always stronger than me, but sometimes if you want to open a jar, it doesn't open. So what do? Hot water. You put it on there, you smash it? Okay. If you want to take a less violent solution approach, you typically, especially if the lid is metal, you bring it under hot water, and what happens? The lid expands more than the glass jar, because the coefficient of thermal expansion of metals is much higher than glass. And then it becomes larger, and then it can open. So, what I want you to know again is that change of temperature, delta T, creates a strain and not necessarily a stress. So it's not like mechanical loading. We'll see in a moment what I mean. And of course, if you have a strain, if you multiply it by the original length, you get deformation. Let's look at this for a few seconds, and then we look at this example together, which I like to spend some time on. Any questions about that? That's the example. So now we have three different bars they're all made of the same material. And you see the difference between A and B is that B is 2 times larger, and C has a cross section which is much larger. Just based on your intuition, which one do you think, if I increase the temperature, what do you think will happen? Which bar will have the largest stress? Now, previously I said temperature doesn't necessarily create stress. And now I'm asking you, looking at that, use your intuition first. Which one do you think will have more stress among the three? Okay, let's go. A. B, C. So the answer is the stress will be the same in all three. And this is what I want to show you. Now, first of all, let's make one thing clear. If I didn't have the other wall here, if these bars were free to deform, there would be no stress. They would just deform. Because nothing would prevent them from deforming. Now, what happens when a bar deforms? The way to solve this problem is to do some sort of superposition. So you say, okay, I apply delta t. And first I assume that there is no wall here. I take it out. And you can calculate how much strain you are going to have for delta t. I just showed you. If there was no wall, remember, this would just deform. Nothing would prevent this from deforming, and there would be no stress. It's a thermal deformation. The atoms, when they get warm, they start to move faster, they increase their distance, and then you get deformation, but there is no stress. But there is a wall, and the wall is actually pushing back to make sure that the length is the same between the two walls. So now there will be a stress from the wall to make sure that it's not going to elongate like that, it's going to stay its length. And this is a mechanical stress, so what we know so far, it's good. Yeah, I think I have a nice one. So if you look at the temperature, the strain due to temperature change, and the strain due to mechanical stress, we have these two. Yes? There are two scalars. So are you taking linear algebra? Because if you have vectors, you can talk about cross products or products, but here we just have two numbers. So for this to stay the same, basically these two have to be equal. So how much elongation you have has to be compensated by how much mechanical strain that you would have had if there was no wall. So this is the story. In a situation like that, you think first, okay, I take the wall off. It will deform alpha times delta t, just because of temperature. But then compressive. And it comes from the wall reaction to this strain. And it is sigma over E. We know how to do that. And we see that nothing changes. This is not going to elongate because this stress pushes kind of this back. So for that to hold, these two have to be equal. Or if you write it, so you can think about it, writing it like that, if it is compression, and just say these have to be equal. Or you may consider this as tension and you write it like this and just say that the summation has to be 0. At the end you get the same thing. And as you can see, this doesn't depend on the length of the bar. It doesn't depend on the cross section. That's why I told you that actually all 3 bars we have the same stress. Also, it is not included. I agree. So thermal loading could be a little bit different. Any questions about this? Is there any place which is not clear? I can explain it one more time just to make sure. So remember that change in temperature by itself doesn't create a stress. So a stress equal to E epsilon does not apply to thermal loading. This is in mechanics. You have to have a load and so on. So if there was no wall, you wouldn't have any stress. You would have this strain and multiplied by L elongation, but no stress. But there is a wall. So imagine you increase the temperature and this bar wants to expand, but it doesn't have a place. So there will be a stress inside. There will be some stress inside because the wall is pushing it back. The way we calculate it is we say, okay, first I take the wall off. This would be the amount of strain that would happen if there was no wall. And then how much is the strain actually imposed by the wall to keep this together? And that is mechanical. Sigma over E. These two, which is actually negative, these two have to be equal, and that gives you the stress. So the answer to that question is all 3 have the same stress. Now, we achieved our goal. We are finished with this package. Remember, at the end of each package, I want you to think about things you've learned and try to write a few things to each bullet. For example, types of loading. How you would calculate normal and shear stress strain. What is the difference between linear, nonlinear, elastic, inelastic? And then what happens when we have elastic or plastic deformation at atomic scale? What happens? And how do, let's say, the brittle and ductile materials differ? So please take a few moments and write down a few things here. We have time. And these are where, for example, there may be some questions from. It's a good place to review and to make sure that you remember what's going on, what you have been learning in the past, in this case 4 lectures. And it has to be your own words. So let's say then you can go further. long one. You can see the front point, the office from the board. And again, when you study the materials, for example, for the quiz on Monday, make sure that you can actually answer all of these in much more detail than what I quickly wrote down here, that you actually understand all of this. That tells you that you know the materials in that package. It's just a good test. And I think it's important that you use your own words. I don't know why, but I think it's important. And then if you look here again, I've listed some of the technical terms that maybe some were familiar to you, some weren't. And this is also a good place to check whether you remember all the concepts. I switch back if you want to look at some stuff. But basically these two slides at the end of each package is to tell you what things are. I'm going to upload also a completed packet, maybe tonight, later, so you have that. Homework is due Friday, so I hope you have started already. Yes. You cannot submit the homework electronically. It is written in your syllabus, and I explained to you why. Because the graders, maybe they don't have an iPad to grade your work electronically. So I will not accept electronic submission. It's not possible. If you have any questions, we still have a few more minutes. Just come, ask questions.
I just like idealize these curves and like made a triangle and a rectangle. Okay.
So this is the reality.
And then also just ask
I know from the diagram and how you explain it, we're saying this. Alright, yeah. So it's mostly this area under this curve, like that's the way
It is here. So it's the area under the linear elastic part.
Yeah.
yeah, I like myself a lot of space.
I can just work out.
Let me show you this. It looks more, I don't know why it looks so bad on your slides. It looks ugly. It's the same as slides. But so you see the difference?
Oh yeah, that makes more sense.
I'm sorry.
No, it's okay.
I didn't realize it looked
I think it's just the way it
so
printed out. Yeah. Okay.
I'm sorry.
So, but the way you would still evaluate this, you would
There's
use
until linear elastic part.
Okay.
And then this one is all the very many pixels.
Oh, okay. Oh, so that's why we were just adding the value.
Exactly.
Okay. And then this is just going to be the area, so you could either use an integral or you could just do the area for like a triangle or either one.
Right.
Okay, good. Thank you then.
I have a question. Can I treat this one as simple as it seems, or should I be doing more with it?
Excellent. stress without plastic deformation. Okay, so you have to check. Here what you have to check is that whether the load that you have, this is when the plastic deformation starts.
Yes.
So you use that, and so the maximum length is
It just seems too easy.
Yeah, right? Because we have this whole
I
page.
think plastic deformation. Don't worry about the
Okay.
page. I think I removed one problem.
Okay. Well, then that makes more sense.
It was something that I thought maybe doesn't work there.
Just assume you like get trends with this, so you see a lot of space and you assume.
Don't assume that when I look at the problem, I know the answer. So I also have to look at it. So please be patient. I'm trying to, don't want to tell you something which is not accurate that doesn't have the strip in LCU. Oh, maximum length. Okay. But this is not delta L. So this is the final length, right? So it 3.28 inches is not. So it is. This is not delta L. It is L. It's L0 plus delta L.
Okay.
So here and then you want to go to the. This should be
So
okay.
just
But
change.
here, yeah, be careful about the wording. And normally deformation is not so big, but.
Do you want these on separate graphs or just the same graph?
Just make sure that it's clear which one is what.
Okay.
Yeah, it doesn't have to be. Yes.
How come the slides is really
Yeah, it's just a plotting, printing functional. So that's why there will be also video and